Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm going to try to explain this idea of supervised dimension reduction from three different perspectives. The first perspective is going to be really a Bayesian or a probabilistic framework where we're going to talk about what this problem means. Then we're going to reinterpret it from a geometric perspective. How do you think about supervised dimension reduction? And the last version of it is, how can we scale this up to very, very massive data? And the idea there will be showing that you can do a lot of these things, but you can reformulate it as a generalized eigendecomposition problem. And so those are going to be the three parts. Okay? So this idea of dimension reduction is really related to an idea of information and sufficiency. Classic notion of sufficiency is I give you n observations from a multivariate normal, right? If you can estimate the mean and the variance, you can throw out all your data. It's a sufficient statistic. So that's going to be kind of the framework or the perspective we're going to take in. This is what I just said right here. Let's see, yeah. And so specifically the model we're going to think about throughout most of the talk is just a regression model. I have y, it's my response variable. X are my covariates or my explanatory variables. X's are very high dimensional. Y can be, let's say, an R. These ideas will work also if y is 0, 1, or 1 minus 1, or multi-categorical. And we'll assume that our noise is 0 mean. Okay? And what we have is we have our data set, x1, comma y1, and observations of these are drawn. IID from joint distribution on xy. Some of these ideas we can actually generalize to non-IID settings, but let's not exactly worry about that right now. So roughly speaking, our idea is going to be that, well, x is very high, it's p-dimensional. I'm going to replace x with some statistic of x, we'll call that theta of x. That's a lot lower dimensional, okay? And somehow this should preserve things. And again, the idea is if you have physical, biological, social systems that are inherently low dimensional, which could be one version of an atom, we can capture these by low dimensional submanifold. And later on, at some point in the talk, when I make some of these results a bit more concrete, or try to quantify a bit more, I'm going to say that the marginal distribution on X is concentrated around a manifold which is low dimensional. But for many of the results, we don't necessarily need that. So again, going back to the regression problem, just what I said before. Let me see. These are my Y's. These are my X's. And my model, Y is equal to f of xi, epsilon I. I'm going to think about that as I can just write this as what's called a semi-parametric model, in that I can rewrite it as a function g, which is in the span of a much lower dimensional reduction. For most of the talk, I'm going to think about dimension reduction as a linear projection. There are ways of extending that. If someone wants to know about that, we can take that offline and I'll show you a few pictures. But again, the idea here is you have this collection of basis sets, B1 up to BD, and the span of this B is called the dimension reduction subspace. Now, I just wanted to show you kind of a picture before we went on, and if you do things like manifold learning, often you show things like the Swiss roll. So this is, again, a picture of the Swiss roll, and what I did in false color is put function values on it, okay? And the idea is there are different types of things. There are projections and there are embeddings. So this is what's called a diffusion map, and what it's going to do is trying to embed this into two-dimensional space. And it's going to try to embed in a way that the first direction is going to be the direction in which there's a greatest spread. It turns out, sorry about that. In this data, the greatest spread is in this direction. So, and not in this unrolling direction, okay? So again, that's why you want to do this supervised. You want to take the information of the false color into the directions that you want to spread. Now, if I were to do a linear projection on this in a way that would preserve the function values, I want to project into a lower dimensional space and preserve the function values, well, the natural way is just to slice it onto the, I'm just going to use this, onto the, basically just slice it, I'm not going to use this, slice this onto this coordinate, right, which is just the x, the xz plane, right? And if you want to do embedding, you can actually even try to do an embedding which will unroll it, but it'll unroll it with respect to the greatest direction of variation. And that's what's going on here. And we'll revisit these. I'll actually show you some pictures of these, okay? So before I tell you about a probabilistic model for supervised dimension reduction, just really quickly want to go through PCA because everyone knows that. Okay, so what do you do when you do PCA? You have your data x1 through xn. You basically construct a p by n matrix. You compute the sample covariance matrix. I probably wanted to divide by 1 over n, and then, or 1 over n minus 1, and then you do an eigen decomposition of this, and then you do what? You collect the eigenvectors corresponding to non-zero eigenvalues, and this is your subspace projection, okay? So how would you think about doing something like PCA if you want to do it within a probabilistic modeling framework? You're going to say your x is a p-dimensional variable. We'll just pretend it's multivariate normal. I'm just going to say, hey, it has some type of factorization structure. So this is its covariates, and then it has some mean, and then I can break it up into some basis set nu, and these are my loadings. Nu are called factors, and A are called my loadings. And what are going to be true of these factors? They're all independent. Okay? So this is just thinking about PCA, but writing it down in the language of a probability distribution. Mu is in RP, A is in P by D. These are my loadings. My covariance, again, is P by P, and nu is in RD. Okay? So now we want to think about the supervised dimension reduction case, much like PCA. And there's and again, right, nu is a latent variable. Okay? Again, this you can consider what we called the atoms in the previous talk as an example of one. So again, we're going to think about the semi-parametric model, and I want to find this B, which is this projection. So this is a very nice idea. This is called principal fitted components, and it's an idea by Dennis Cook. And it, in a way, just generalizes PCA. It says, let me define x sub y as x given y is equal to small y. Let's make this concrete. Let's say y takes two values, 0 and 1. This is going to reduce down to something that looks like linear discriminant analysis. So all we're saying is if y is 0, I have a particular distribution on x. If y is 1, I have a different distribution on x. Okay? And all I'm saying is for these two different distributions, I have the same loadings. That structure is the same. I have different means. Okay? That's all this is saying. And then you can rewrite, this is mu again, it's p-dimensional. A is my loadings. V sub y are my, in this case of 0 and 1, are going to be my two different basis sets. One's going to explain, let's say, class 1. The other one's going to explain class 2. And then what you can do is you can say that this projection space B, you can work this out, is just the inverse of the covariance times the loadings. Okay? One of the things we're going to see throughout this talk is this idea of identifiability is going to be revisited. And what I mean by that is that I cannot tell you exactly what sigma is versus what A is. I can tell you together what the projection could be, but you cannot uniformly separate these two. Okay? This is works quite well if I have global linear predictive structure, same as PCA. If you have global linear predictive structure, it does quite well. But if you have clusterings or manifolds or some localized structure, it doesn't do very well. So anyone want to take a guess how you deal with this? So in manifold learning, one of the key ideas people have basically stated, well, manifolds are locally Euclidean, right? A natural extension or analog of this in probabilistic modeling is you just go to mixtures. So instead of having one Gaussian, I'm going to have a mixture of Gaussians, or a mixture of some distribution that is unimodal. Okay? And this will let me capture quote-unquote non-parametric distributions. So how do we go about doing this? Well, okay. Similarly as before, I have x sub y. Actually, let me draw a picture. Okay? So let's think about this case. Let's say that I can write on this, right? No. Okay, so this is my data. Let's say this is class 1, this is class 2. According to the previous estimate, what would I do? I get a mean for this class, which would be right about here. I get a mean for this class, which would be right about here. This is degenerate and kind of useless. Okay? So what you're going to say now is, well, I'm going to index these means, right? These nu sub xy's, right? These latent variables, both in terms of x's and in terms of y's. So what you're going to do is you want one cluster xy here, another cluster xy here, another cluster xy here, another cluster xy here. You put these together, you get the plane back, right? Which is not any dimension reduction, but if you want to explain this without loss of information, you need the plane, okay? So that's basically all you're doing. You're just saying that I'm indexing these y's, right? These zeros and ones in this case, by multiple clusters, okay? And it's the similar model as before. This is an RP, this is my covariance structure, these are my factor loadings, and then what this is doing is this is giving me the factors, right? And so these factors are locally clusterized. Okay. Now, again, you can show in this model the dimension reduction space is simply the span of sigma inverse A, and by that I just mean y given x is equivalent in distribution to y given B transpose x, meaning if we estimated B, we could basically just throw out our data and work in this much lower dimensional projected space, and I have the same predictive distribution. Okay. Great. So how do we go about doing this? So we're going to go about doing this by Markov chain Monte Carlo, and just what I mean by that is you have a likelihood. I'll tell you what that is in a second. We're going to put priors on the various stochastic quantities we want to look at. And then I'm going to give you a Markov chain, which is going to be transitions between these different parameters. And the stationary distribution of this Markov chain will converge to the posterior distribution. That's all I'm saying. Okay? So first we need a likelihood model. So this, again, sometimes it's called inverse regression, because you're building a model for x given y, right? And the other parameters, the mean, the factors, the factor loadings, and the covariance structure, right? And we're just saying this, again, is normal. And this mean comes from really a collection of clusters, okay? So in the case where you have a categorical response, a very natural way of saying this is that, let's just make it simple, okay? A really natural way of saying this is I have C categories, right? So nu sub I could just be a Dirichlet distribution, right? Because I have a multinomial, and I just want to say which one of these belongs to these C categories, okay? If you want to make it non-parametric, you can actually use a Dirichlet process, but again, that's more of a detail. And again, this is a case with a Dirichlet process, but you can do the same thing with a Dirichlet distribution. So this is, again, is, this is my likelihood right here, and I can just rewrite it in this form. And then this is what I'm saying before. I want to get the posterior of these parameters theta, and again, that's just going to be proportional to the likelihood times my prior. And so one of the things that's nice about this, it's not just going to give me one subspace B, it's going to give me a distribution over subspaces, so I can have some notion of my uncertainty in these estimates. Okay. And so the way we go about doing this is my parameters theta correspond to the mean mu, the factor loadings A, the inverse of the covariance, and the actual factors. Okay, T is the iteration of the algorithm. And so what I can define is theta with the slash mu means I just took out the mu parameter. Theta slash A is looking at all parameters but the A parameter. Similarly, this is looking at all of them but the covariance, and this is looking at all of them but the factors. So you run this, and basically for most of these parameters you can write down very simple probability distributions because the marginals are very simple. It's what's called a Gibbs sampler. If I condition on one of the variables given the others, they follow nice probability distributions, okay? Sampling these VTs is a little bit more involved. So this is a little bit trickier. But the bottom line is you can do this. Now what's interesting is, what does this give me? It gives me an estimate at each iteration of this inverse covariance matrix. It gives me at each iteration these factor loadings. Put those together, and what do I get? I get a projection space, right? Now we know that these spaces, these projection spaces, have a natural geometry, right? These are points in what's called, each one is a point in what's called the Grassmannian manifold, right? So what you can actually do is say that, okay, BT is, again, I said a point in the Grassmann manifold, and there's a natural Riemannian metric on this manifold, and this has two implications. The first implication is that since I have posterior estimates of t of these, I'd probably want to find the mean and look at the variance of them, right? So what's a natural way of looking at the mean? You don't want to average all the elements in these subspaces because that's not the natural distance or geodesic, right? So you can actually compute the barycenter in this case because you know this geometry. And similarly, once you compute the barycenter, you can get the variance, okay? So how can you compute the barycenter? One way of doing this is by something called the Karcher mean, where if I have two subspaces W and U, I write down the orthonormal basis W and V, and this is just basically what the Karcher mean is. It's a lot of equations for really saying it's the angle between the subspaces, right? And that angle, you're really looking at this, getting from this arctan of this SVD on it, okay? So given my observations B1 up to Bm here, actually not my observations, my posterior estimates of B1 up to Bn, I can find basically the barycenter of them. And that's my Bayes estimate. And I can also tell you the uncertainty. I can tell you this is the variation I have in my estimate for this type of model. Okay? Another thing you could, I'll come, yeah.
Do you take distance squared or distance of power 1?
We take, good question. I think we take distance, we don't take distance squared. But it might make sense to take distance squared, yeah. So I just want to show this on some data, just again to show you what you can do with this. So if anyone cares, this is the equation for the Swiss roll. I have 3 dimensions that are relevant and then the rest of them are noise. And then I'm just placing a function on the Swiss roll. That's how I got my false color as before. And this is just a picture of what it looks like. Now, we know our estimate of the space B hat, right? We know the true space B. And so I'm just going to look at the projection of B onto B hat. That's all this equation is telling me. I'm going to use that as my metric for how far these subspaces are. And what I'm just showing you is for a bunch of different algorithms what these results are. And let me just talk you through this. Okay, so these algorithms down here, I'll return to them actually. SIR and LSIR I'll actually return to. These are basically algorithms that only capture linear structure. Right? The projections are linear and the structure that they can capture are linear. They can't capture clustering structure. They can't capture these other things. So as my sample size increase, if I ask about the accuracy of the subspace, they improve but not so well, okay? This is this Bayesian algorithm. It does pretty well. And then this is an algorithm, the squared, which is much simpler and scales a lot better, which I could probably get to do that well, just this parameter setting, and we'll come back to this. But again, this also is doing something localized. But the bottom line is, when you do something localized in this type of problem, it really does help. One of the relevant things,
Your accuracy, so you cannot use the form of a manifold and you check how far.
Exactly. Here I know exactly what the projection space should be, so I'm asking you how far it is, okay? And one of the things that's nice here you can do is I can actually give you a posterior estimate of the variance, right? So I can tell you this is my projection and I can give you my notion of uncertainty on the projection. One of the things I didn't tell you is how to estimate how many factors or how many components there should be D, right? Within a classic Bayesian framework, there are certain model selection criterion approaches to do this. They don't work in this problem. And if anyone wants to talk about that in more detail, I'm happy to tell them. So we just it's very simple cross-validation, which did tend to work. An example on more realistic data is the digits data set. These are 3, 5s, and 8s. And what we looked at are 2 classification problems, 3 versus 5, 5 versus 8, because these are some of the harder ones. And what I just want to show you is, okay, we have 100 training samples from each class. And I kind of like this picture. Let me just go through this picture, okay? These 2 pictures are the projection spaces for, this is for 3 versus 8 and 5 versus 8. Okay, so if you think about it, if you think about, I am really not good with this. If you think about 3 versus 8, this is a 3 and this is an 8, right? And so you ask which points or what areas are going to give you the difference. And well, it's right around here and it's right around here, right? So again, this is the posterior Bayes estimate. Again, 5 versus 8, this is a 5, this is an 8. What region is different? It's that little slight diagonal. So, visually, this is somewhat interesting and appealing. Now, if you apply this to a multi-class problem, which is trying to tell apart all of the digits, and you compare the linear Bayesian model to a nonlinear Bayesian model, and this will actually generalize to other types of linear versus nonlinear models. Not surprisingly, you see the nonlinear one does better, and the bigger differences are in the 8s and the 5s and the 3s, which is one of the reasons I picked those. Okay? How do I cluster them? So here, I have a classification problem, right? There are 10 classes, 0, 1, so forth, right? And so in that model, right, instead of, I could write down a likelihood as a multinomial, right? And then just do what I did exactly before. And if I want to classify them, there are different ways. One way is I could use within the model. The other way, I could project down and do k-nearest neighbors. Okay? So this is an old data set. It's a cancer classification data set from gene expression data. You have 7,129 genes. 19 samples come from one class. 19 samples come from another class. We know that this second class falls into two subclasses. So if you run this and do the projection, what's interesting, you get this blue, which is this one class. And then without telling the method that there were these two classes, it actually separates them out. So again, this is kind of nice. Some of the interesting problems that are still open here are how do I do direct inference on the manifold? The way I solve this problem is by pushing it through a factor model, right? Instead of pushing it through a vector model, I could have said, well, there is a subspace. Can I do direct inference on the subspace? I can write down a likelihood with respect to the subspace. Can I do direct inference there? What happens if I have a mixture of subspaces? Can I pull that out? I mean, this is something that Gilad's worked on. There's a very interesting differential geometry problem, which is if I don't know the dimension of the subspace, let's say I have a Grassmann of dimension 10 and one of 11, the geodesics are infinitely far apart. That's not very helpful for me when I'm doing inference because I kind of want to say these two are closer, right? So how do we get the math to kind of work out right with the inference problem? Just like there's a natural geodesic on subspaces, there's a natural geodesic on covariances, so again, that problem can be thought of that. And I'm going to come back to this. Can we adapt this to scale up for very massive data where a Bayesian method that's doing MCMC maybe is not the most feasible idea, okay? And then again, mixtures of manifolds. Okay, so I think I've showed you this before. From now, assume that the marginal distribution on X is concentrated on a low dimensional manifold. And what I'm going to do is give you a geometric perspective of this problem, okay? And what I'm going to say is an important quantity is going to be the gradient of the regression function. So my regression function is f of x. And so I'm just taking coordinate-wise partial derivatives and then lining it up as a column vector. Now an important idea or quantity is what's going to be called the gradient outer product. So this is a matrix gamma. Each element of it, ij, coordinate-wise, is nothing but basically the inner product of these different coordinates with respect to the marginal distribution. So we can write it like this, or you can also write it in terms of a cross-product form. Now if you think about this and you do some calculus, you say, okay, this is f of x, okay? It has this parametric form. There are really only d subspaces or relevant directions. So here I have b. Okay, if I solve the eigendecomposition on the gradient outer product, okay, those are going to give me, let's say, my bi through whatever bd. So now what I say is take the directional derivative of f with any of these bi's, right? This is what the form is going to be of this, right? And it's not going to be equal to 0. However, if I take any direction w that's orthogonal or outside of bi, right, then this product, this quadratic form is going to be 0. So from basically a very simple calculus argument, you can say that at any point, really, the gradient is giving you the dimension reduction information. Now, let me restate what I just told you, but from a more statistical perspective. Let's pretend for a second my function is linear. Okay? So then I can define here, this is called the covariance of the inverse regression. So you're really asking about x given y, right? The expectation of that in the covariance. So this is telling me how does x vary as y varies along different directions. Right here, this is nothing but the covariance of x. And then you can basically show that this gradient outer product, just ignore this is just a constant, is really this covariance of the inverse regression, right, sigma, modded out by the directions of the covariance. So you're saying, hey, show me the directions in which x vary with y, and divide out or mod out the directions that x just varies naturally by itself, right? That's all this thing is doing. Okay, so how do we think about this when f is smooth but not necessarily linear? So the idea is, well, intuitively you could say I can take my marginal distribution, rho of x, I can chop it up into little partitions, psi of x, and within each partition I can compute the covariance of the inverse regression, my covariance and my variance, and here I have the mass in that partition. And then you can show that basically the gradient outer product is just the sum of this, right? So what you're really looking at is in each region you have a rank 1 matrix, and you're just averaging all these rank 1 matrices in terms of the mass in that region. And if there's not great variation, then what can you do? You can project down to very low dimension. If you really need many, many rank 1 matrices that are quite orthogonal, then you're going to need more of your space. Okay. So one way of thinking about this is I can take y as f of x, basically. Then I can think about the gradient here at xj. I can Taylor expand it. And so what I can say for any xi close to xj, this is my Taylor expansion. And f vec is just my estimate of the gradient. And wij is just a weighting. If 2 points are close, wij is going to be close to 1. If 2 points are far apart, they're going to be close to 0 because the Taylor expansion only has a region of convergence. And so again, you can try to actually estimate this gradient as a least squares problem with the regularization. There is actually a variety of different regularizations in the literature. We used a reproducing kernel Hilbert space, but there are other papers where people used kind of L2 on linear estimates of these gradients. And then what you can show is if the marginal distribution is concentrated in a compact Riemannian manifold that's d-dimensional and there's some isometric embedding, if the density is Holder continuous, if you're estimating derivatives and there are parts where the density goes to 0, it's a bad news for your derivative. The other condition you need is the measure along the boundary is small. Then basically what you can show is our gradient estimate, f vec on data. This is a p-dimensional object. Del sub mf, this is my gradient on the manifold. This is a p-dimensional object, this is a d-dimensional object. What d phi star is doing is pulling this p-dimensional object back to the d-dimensional manifold. Okay? This in terms of an L2 norm on the support on the manifold, this convergence rate is not in the dimension of the ambient space, but in the dimension of the manifold, is a basic message, right? So in the manifold case, you can actually show that it's actually, the convergence rate is much faster. So in the last 5 minutes, I wanted to tell you about another way of thinking about this, which scales to very large problems, okay? Now, I told you before that there's this notion of the inverse covariance of the inverse regression. This is this omega. This is simply my covariance. I can solve this eigendecomposition problem. If my data is nicely linearly separable, or is the version of supervised dimension reduction, which I said corresponds to PCA, what are these v sub i's going to give me? They're going to give me the directions in which I get a good amount of variation in the covariance of the inverse regression, but not a huge amount of variation in x, okay? So this is an old algorithm. This is called sliced inverse regression. And it's by a person named Kerchow Lee. And basically what you can say is, okay, my subspace B is just the span of those VIs for which there are non-negative eigenvalues. How do I implement this given data? Well, first I just estimate my covariance. Then what you do, it's called sliced inverse regression. You take your values y, you slice them into little bins, and for each bin, you compute a local mean. In each bin, you compute a mean, and then what do? You basically take the rank 1 matrix for these means, and then average them over all slices, okay? And then you do the eigendecomposition, and then you look at those eigenvalue vectors corresponding to eigenvalues that are a little bit bigger than 0, okay? This works well, again, in the PCA type case. What do you do when your data has nonlinear structure or clustering structure? Anyone take a guess? You change this step. You compute local means. So there's a variation, just what I said here. I'm going to do the same thing, right? I sliced my data, but for each slice, for each point I, I'm going to look at its j or k nearest neighbors, right, that live in that same slice. And then what I'm going to do is I'm going to compute a local mean based on those k nearest neighbors in that partition. And then I just do the same thing. I compute this gamma hat in terms of the sums of these rank 1 matrices. I think this should not be a double sum. I'm sorry about that. And then you solve this, again, this eigendecomposition problem. And this works well if you have nonlinear structure. It's much like the Bayesian model that I told you with mixtures, right? Instead of doing mixtures, I'm doing k nearest neighbors to do the localization here. And again, this is how you get beta hat. Now, if I were to do a straightforward Koleski factorization of either the sliced inverse regression or the localized version, it's going to be order n squared p, which could be bad if n and p are really, really big. So how can we do better, right? And here you can actually use some of the very nice results from randomized SVD to do this. And we'll talk about that. Now we're going to assume that this omega hat, right, this covariance of the inverse regression is low rank. If it's not low rank, then there's not going to be a low dimensional projection that's relevant. And so then what do? I can think about it, I can basically do an SVD of it, right? Then I can break it up into 2 different parts. And I'm going to try to rewrite this generalized eigendecomposition as follows, right? So here, this is the same as this. But what did I do? I basically divided out by the omega hat, right? Is all I did. I divided out by the omega hat, so I still have my sigma hat. So I can think of this eigendecomposition problem. This lambda is still the lambda we have there. And my basis set are going to be omega hat 1/2 vi, right? And then I can transform this back into the original data. Now the question is, what's the advantage of doing this type of decomposition? And I'll show you that very, very soon. The advantage is going to be this matrix that I'm going to construct here can be constructed quite quickly, right? And it's not going to be this order n squared p. Okay. So in the case of sliced inverse regression, I order my data, let's say in terms of y, and I slice them. And for each slice, I can just basically say, okay, the points in this slice all have values 1. The ones that aren't all have value 0. Okay? And then I can define a matrix J, which is just basically diagonal matrix of each of these slices. And then you can show that omega hat is nothing but, this should be capital X transpose J transpose JX. Why? Because in each slice you're just looking at a rank 1 matrix, and you're just basically adding these over all of the slices. And what do you know? Well, the rank has got to be less than h minus 1, which is a lot smaller than n and p. So already there you have a benefit. Now, if you're doing the localized version, then you're going to again construct these block matrices for each slice. And in each slice, if xi and xj are k nearest neighbors, you just write down 1 over k. Otherwise, you write down 0. And then you define this matrix J, which is basically this block diagonal matrix. And then again, you can write down omega hat in terms of this block diagonal matrix. So now what you can do is, I'll just tell you this case for SIR, because SIR is actually simpler, is a randomized SVD on X is just going to be order NP times L. L is more or less my guess of how many factors there are, plus a little bit of a fudge factor. T is a number of power additions you do in a Krylov subspace method. Constructing this gamma hat now is pretty cheap. It's KNP. The RSVD of this omega hat again is like this. So the total complexity is TL plus K times NP as opposed to order n squared P, which could be quite a bit. There's another interesting thing about this. And there's people who do regression using factor models. There's this old problem which is called the least eigenvalue problem. Let's say you're doing regression. But first you do PCA. And it turns out all of the signal in your regression is in your lower eigenvalue, the eigenvectors corresponding to your lower eigenvalue. This is called the lowest eigenvalue problem, right? What you noticed is if the signal is contained in the lower eigenvalues, it turns out that this randomized approach will do better than the exact approach. And kind of the argument for this is that this randomized approach is actually, in a way you can think of it's regularizing or putting a prior on the decay of the eigenvalues, right? It's doing it in a particular way. And so it's actually modeling this, your estimate of the covariance matrix rather than using the sample estimate. And there's a benefit to that. And not showing it here, but you can actually make that a little bit more concrete, and we have some of that using simulations. And these are people who gave some money for this, and this is very much ongoing work, so if I stated the open problems or the open things we're thinking about, it would be really long, but I'm happy to take questions on them. And that's it.
I'm not sure I understand exactly all of that. So you have some manifold which is lower dimensional and higher dimensional space, and you're going to Gibbs samples to find out your variance correlation matrix given the samples, but knowing that it lies in the manifold, right?
So almost. So what I'm saying is that I have this data. It has some low rank structure, or could be a mixture, right, of these low dimensional manifolds, okay? And then what I want to find is a subspace that's going to contain all of the directions of variation on that manifold that are relevant for the prediction.
But on that manifold, it could be anywhere.
It could be anywhere. It could be anywhere.
And for that, you're doing Monte Carlo approximation.
Yeah.
But the manifold is weird. You won't mix the electrons.
I'm sorry?
The convergence rate depends on how the manifold is.
Absolutely, absolutely.
Where was that reflected? The curvature and so on.
Exactly. That's exactly correct. So so when I gave you the analysis in terms of the gradient, I didn't do it for the manifold, the MCMC algorithm, right? We haven't fully done the analysis of the MCMC algorithm, but you're right, there will be a few things, right? One will be the curvature of the manifold, which will directly relate to how many of these subspaces there really are. If I have many, many subspaces, right, then what's going to happen? This Grassmannian is going to be quite high dimensional, right? So sampling from that's going to be a huge problem, right? And so that's how that will be manifested, right? Because you can think of these as patching together low rank matrices.
That's right.
Yeah, exactly. Yeah. So it'll show up there. And what you can try to do is you can do a theoretical analysis. You can also look at one of these MCMC trace plots of each run, look at your estimate of beta hat of the subspace, right? Look at the geodesic distance of that, and then you can see how sticky or how bad that is, right? As your trace plot of the MCMC. And in the case where the manifold is badly behaved, that's a mess. Absolutely.
How do we decide how many points to put in a local neighborhood?
Okay, so this is a question. How many points to put in the local neighborhoods? So
Actually, which of the points? Could be the number of points for each neighborhood.
right. So the way that we get around that is in this localized sliced inverse regression algorithm is we just fix k, right? And for each point, I'm just going to be looking at locally k. Now, if I sent k to 1, it turns out that I end up with PCA. If I send k to all of the points, I end up with sliced inverse regression. So in a way, it's kind of interpolating between PCA and the global case.
This choice can be potentially very crucial.
Yes.
Paper Grassmann shows that all you have to do is figure out the right k for your thing, then algorithms as simple as k and n would automatically adapt to manifold.
This is absolutely true. So this is absolutely true. I think because we're averaging over all of the endpoints, we're a little bit less sensitive to k because again you're averaging all of these local neighborhoods, right? Now, how can you select k more rigorously? There's work on that. There's multi-scale PCA work on that. My colleagues at Duke works on this. There's a variety of ways of trying to think about that, right? But the basic question you really want to ask is within this local neighborhood, right? Have I captured that linear substructure and have I not gotten too small? So I want to capture the biggest chunk I can, right? Such that I get that linear substructure. One way of thinking about that linear substructure is just I'm capturing the tangent plane in that region, right? Things more or less effectively linear, and I want to capture that rank 1 linear structure, and that's going to be plus or minus my tangent plane. And make the space, that region, as big as possible that I get that, because if it's as big as possible, I'm estimating it okay. The one thing that we're doing which is good is instead of chunking them separately, we're averaging them, right? Which gives us a little bit more robustness.
So the work of your colleague actually is more for linear sample sets or pictures.
Yes, it is, yeah. But you can try to use that for each section if you want to. I don't think it's worth it. Yeah. I wouldn't use it for this.